on the natural numbers, which is what I've done here. And so that's the auxiliary function, that's the decreasing on the natural numbers. And then decreasing z1 of n is just convert the zn to a natural number. And then each element of the list will convert the natural number back to a z. And now we'll get exactly the list of integers we want. But if we use this definition, we have another problem. That when we do induction over our decreasing function to process this list of natural numbers, excuse me, the list of integers we get, there's all these conversions from z to nat and nat to z, and it's very clumsy to work with those conversions. Why is it clumsy? It's not Cox's fault exactly that it's clumsy. It's that when you convert z to nat, then for your own sanity, you had better prove that the z you're converting is non-negative. And so we're back to the clumsiness of natural numbers. We want to completely avoid the natural numbers when we're doing these kinds of things. So, what we want is a function instead of a fixed point. Now, a function is a sort of defined construction in Coq that in the end reduces to a fixed point over proofs of well-foundedness. But let's think of it at the user level. It's a recursive thing where your proof of well-foundedness is not through structural recursion, it's through a proof that you provide separately. Okay? So we say function decreasing of n, which is a z, is if n is greater than 0, then n cons decreasing n minus 1, else nil. That's what we want. And we have to provide this extra sort of directive that there's a measure that decreases on this argument n. And a measure, well, it's a function from whatever the argument type is, in this case z, to the natural numbers. And we have to prove that at each recursive call, this measure function applied to the argument is smaller than the measure function at the formal parameter. Okay, so let's do that. There's our function definition. When you say fixed point, you're done. You've defined something. When you say function, it gives you proof obligations. Basically, as many proof obligations as there are recursive calls in the body of your function. And the proof obligation here, if we look at it, is to show that the measure applied to the argument at the recursive call is less than the measure at the formal parameter n, which is to say the measure function is z dot to nat. The recursive call was at n minus 1, and the formal parameter was n. So we've got to prove that. We search for some useful thing about a z dot to nat and less than, and we find injective less than. So this will be provable if all these things are true. If the two things that we're applying z dot to nat are actually non-negative, that's the kind of proof obligation that shows up all the time when you deal with z to nat. And the original thing that n minus 1 is less than n. So these are all provable by omega. And now we have defined the function. Okay, so we have our decreasing function. Now, we want to prove that decreasing 5 is the fifth triangular number, that is 5 times 5 plus 1 over 2. And we're going to do that by some sort of induction. And we could do it by induction on the list, but actually we want to do it by induction on z. But z is not inductive. Or rather, it is inductive, but it's inductive in this way, which is not the way we intend our induction to go. We want the usual form of sort of a natural number induction, but we want it on z. And to do that, we can define an induction principle. So here's a lemma that's just an induction principle for natural number induction on integers. For any predicate, a predicate on integers, if that predicate holds on 0, And for any strictly positive number, if the predicate holds on I minus 1, then it holds on I. And if for any, then for any non-negative number, the predicate will hold on that non-negative number. So that's the induction principle. If we had this induction principle, we could do induction. And now we just prove the induction principle. So, we rewrite by the Z to nat identity conversion lemma that if we convert a natural number to an integer and then back, we get the same thing, which is not true in the other direction. And now we have a natural number that we can do induction on. So we can remember Z to nat n as j, forget how j was defined, and now this is our proof goal, and I'll leave the rest as an exercise. So, I think I'll stop here talking about integers. The summary of the digression on integers is this. When you want to prove things about arithmetic or about programs that use arithmetic, it's more fun to do in the integers than the natural numbers. So you should use the Z type to represent things. Although the Z type is constructed in Coq, you should generally ignore the construction and just use the proof theory. And keep the natural numbers out of things, even when you have to do induction. All right, so I think I will wrap up this lecture. You can download Verifiable C and try it yourself. You can do the exercises in the Verifiable C volume of Software Foundations that we really can prove C programs correct. Any questions? Yes?
What makes verifying or proving things about security properties of hash functions hard? Why don't we know how to do it?
Okay, so the question is, why does nobody know how to do this proof right here, that SHA has the appropriate cryptographic security function, a property. If you look at the SHA algorithm, it's just shuffling the bits around and looking up the shuffled and XORing them in funny ways and looking those up in lookup tables and then doing some more shuffling. And what we want to prove is that the adversary, who can only do 2 to the 107, 2 to the 100 steps of computation, will have a probability of finding a collision in that hash function of less than 2 to the minus 70 or whatever. So, mathematically, people know how to reduce certain things to factoring, and they don't even know how to prove that factoring is hard, but at least they can do the mathematical reduction to factoring, because there's some nice mathematical properties of the number theory of prime numbers. And similarly with elliptic curves, people can prove reductions in sort of the algebra of elliptic curves. But for the symmetric key hash functions and encryption algorithms like SHA and AES respectively, that don't rely on number theory really, but bit shuffling, nobody has even an approach that I know of to think about this. I don't know how to prove it. You don't know how to prove it. Turns out nobody knows how to prove it. But algorithms like AES and SHA have apparently stood up for a long time to attacks or approaches to attack. And even when AES was, there was a competition 20 years ago for the replacement for the previous symmetric key encryption algorithm. And the judging committee, which was a whole bunch of cryptographic experts, thought about all the attacks they knew of, and it appeared that AES resisted them all. There was the attack they didn't know of, which was cache miss side channels. Cool thing about AES, you know, is that the control flow is oblivious of the data because it's all array lookups. But that just means the array cache misses are not oblivious of the data. And that's proved to be a big problem. And that's why your chips from AMD and Intel and so on, your processor chips, have a built-in AES shuffle algorithm. It's not particularly only to make it faster, it's to make it side channel resistant. All right, anyway, it's just an unknown, right? It's an open problem in cryptography, either to prove this function about SHA or to devise a similar kind of symmetric key cryptographic hash function for which you can prove these hardness properties. Hardness results are hard. Other questions? Yes?
Do people in the cryptography community believe in proofs?
I'll phrase it a different way. Are people in that community willing to accept papers to good conferences about this stuff? And the answer is yes. Right? So in 2017, we published a follow-on result about cryptographic random number generation that involved some of the same people, except this time the undergraduate did sort of this entire level of the proof because she was ready to do proofs about the computational monad of probability spaces. And that paper was published in ACM CCS. So I think the crypto community is definitely receptive to these things. There's a workshop called HACS, High Assurance Crypto Systems. And for the last few years, they've been inviting people from the COC and DeepSpec communities. As Adam Chapala may or may not have mentioned when he talked last week, if you use Google Chrome these days, you are using an implementation of elliptic curves synthesized and verified in COC and then plugged into the Chrome browser. And that's partly because highly optimized implementations of elliptic curve calculations are complicated to get right. And the crypto experts don't generally trust them unless you can do a COC proof, which is, that's where that community has gotten to by now.
Can I add something?
Yes?
I think one of the first papers published about COC proofs at CCS, I think, was considered the best paper. So you can look it up. I think it's a paper by Gilles Barre and his team. It was the best paper in the crypto context.
Yeah. Other questions? Yes?
So on the slide with the graphs of the dependencies of the HMAC proof, yeah, this one. Is the trusted code base the statements of 14, 15, and 8?
Well, it's the trusted code base here. Let's see. It's certainly 15. It would certainly include 8. Because of this gap, you would have to include number 1. And then, depending on how you think about it, you might have to include the API spec of how the C client of this function is going to call it. All right? And then, depending on what you think, so when I hash using this algorithm, it's usually for the purpose of sending the hash code to somebody else. And they would like to know that I'm using the same standard for hashing as they are for checking it. And that's number 2. So, you know, there's different ways to interpret the trusted base of this. In the paper, we point out that the trusted base, well, it doesn't include the CompCert compiler, but it includes, well, the CompCert compiler is extracted to OCaml, so it's got to include the OCaml compiler. The OCaml compiler has a garbage collector and runtime system programmed in C, so it's got to include whatever C compiler compiled that. And you could imagine compiling that with CompCert, but then I refer you to Ken Thompson's Turing Award lecture. You know, once you start looking too closely at your trusted base, it gets problematic. If you're interested really in what's the purest possible trusted base for a machine check proof about a C program, I will humbly refer you to my own paper from about 12 years ago called A Trustworthy Proof Checker. And that worked very well for the 12th system. It would be more of a challenge to do it for Coq, but the same kind of approach might work. Other questions? All right, let's stop here.